in this next video, what I'm going to focus on is I'm going to go to difference and difference estimator, but now I'm going to give you a graphical representation of it and talk about the identifying assumption. Okay, the main identifying assumption is the parallel trend assumption. Okay? So identifying assumption is parallel trend. Trends assumption. What it tells us is that in the absence of treatment, the treatment, the two groups would have evolved in a similar way. What does that mean? Say, for example, these two groups had differences among one another, right? So one group was, 5 units better on average than the second group before the treatment. What you're saying is that if the treatment did not exist, these differences would have remained, okay? So one of the group would still be 5 units better than the other, whatever those units are measuring that y variable, okay? This is the parallel trend assumption. Sometimes you're also asked to test the random assignment. Was the treatment randomly assigned? Well, to test that, what you have to do is test this parameter here. That coefficient, beta 1 hat, the estimator of that, will tell you the average differences between the treated group and the non-treated group before the treatment. What do you expect those differences to be if it was truly random? You expect them to be 0. So if it was truly random, we should expect this beta 0 to be 0. So H naught, treatment was random, is equivalent to saying beta 1 is equal to 0. Okay, those two things are equivalent. Now, note one thing. The parallel trend assumption does not require beta 1 to be 0. It simply requires that the differences, whatever they are, that are captured by beta, still hold. So you could still have the parallel trend assumption holding without having a random assignment. Okay? So that's an important bit to do. And in the second part of this video, what I want to do is give you a graphical representation for this. Okay?